December of 1915, on the Eastern Front of the First World War, a 42-year-old German artillery officer sat in a trench doing mathematics. His name was Karl Schwarzschild. He was the director of the most prestigious observatory in Germany, but he had volunteered for the war at an age when nobody expected him to. His job was calculating trajectories for long-range artillery shells, and between barrages, he was reading a paper by Albert Einstein that had been published only weeks earlier. The paper described a new theory of gravity, one that replaced Newton's elegant simplicity with 10 coupled, non-linear, partial differential equations, so difficult that Einstein himself could only solve them approximately. Schwarzschild solved them exactly, from a trench, under fire, while dying. This was not some narrow specialist who happened to stumble onto the right problem. Karl Schwarzschild was arguably the most versatile physicist-astronomer of his generation. Born in 1873 in Frankfurt into a prosperous Jewish family, he published 2 papers on binary star orbits at the age of 16. He earned his doctorate summa cum laude at 22, became a full professor and observatory director at 29, and by 1909 held the most prestigious astronomical post in Germany, director of the Astrophysical Observatory in Potsdam. His contributions ranged across photographic photometry, radiative transfer theory, electrodynamics, and non-Euclidean geometry. In 1900, 15 years before Einstein published General Relativity, Schwarzschild had already proposed that the geometry of physical space might not be Euclidean. According to Wolfgang Pauli, he was the first to introduce the correct Lagrangian formalism of the electromagnetic field. He was elected to the Prussian Academy of Sciences in 1912. When he volunteered for the army in August 1914, he was over 40, and nobody expected him to go. He was commissioned as a lieutenant in the artillery, assigned first to a weather station in Belgium, then to France, and finally to the Eastern Front in Russia. His military role was calculating trajectories for long-range artillery shells. He was awarded the Iron Cross, and between those calculations, he read Einstein. He had developed pemphigus vulgaris, a rare autoimmune disease in which the body's immune system attacks its own skin and mucous membranes, causing severe, painful blistering. The disease disproportionately affects people of Ashkenazi Jewish descent. Blisters had started forming in his mouth while he was stationed in Russia and was spreading relentlessly. In his era, there was no treatment and no cure. He had months to live, and he knew it. And in those months, between the artillery trajectories and the disease eating him alive, he produced 3 papers that would reshape the universe. One of them contained a solution so clean, so elegant, and so disturbing that the greatest minds in physics would spend the next century trying to prove it could not possibly describe anything real. They all failed. Schwarzschild wrote to Einstein on December 22nd, 1915. He enclosed his exact solution to the gravitational field equations for a point mass and closed with a line that still echoes. As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas. Einstein wrote back a week later, stunned. I would not have thought that the strict treatment of the point problem was so simple. On January 13th, 1916, Einstein presented Schwarzschild's first paper on the gravitational field of a point mass to the Prussian Academy of Sciences. 6 weeks later, on February the 24th, he presented a second paper, this one on the gravitational field inside a uniform density sphere, which established what is now called the Buchstahl bound, meaning that a stable fluid sphere must have a radius greater than 9/8 of the Schwarzschild radius, or gravitational collapse becomes inevitable. 6 weeks after that, on March 30th, a third paper, this time on quantum theory, providing a complete treatment of the Stark effect, the splitting of hydrogen spectral lines in an electric field, using Hamilton-Jacobi methods and action angle variables. 3 major papers in 3 months, spanning 2 of the most important areas of 20th century physics, all written by a man who was running out of skin. By March, Schwarzschild was invalided home from the front. He spent his final weeks hospitalized, likely in Potsdam. Karl Schwarzschild died on May 11th, 1916. He was 42 years old. He was buried, at his own request, in the municipal cemetery in Göttingen, the university town where he had once worked alongside David Hilbert and Hermann Minkowski. His grave is still there. Einstein wrote his obituary for the proceedings of the Prussian Academy, but his solution survived him, and the thing it contained, the thing nobody wanted to believe, turned out to be one of the most extreme predictions in the history of science. Buried inside the mathematics was a radius, a specific distance from a point mass at which something catastrophic happens to the fabric of space-time itself. Cross that boundary, and space and time switch roles. The direction toward the center is no longer a direction in space. It becomes a direction in time. And just as you cannot stop moving forward in time out here, you cannot stop moving toward the center in there. No force in the universe, no engine, no amount of energy, nothing can prevent you from reaching the middle, where the mathematics says the curvature of space-time becomes infinite. The question Schwarzschild's solution forced on physics was simple and terrifying. Is there anything, any law of nature, any physical process, any conceivable mechanism that prevents gravity from winning completely? Is there a flaw, a failsafe, a point where something stops the collapse? That question consumed a century, and the answer, every single time anyone checked, was no. There is one more thing worth understanding before we dive into that century of resistance. Schwarzschild did not predict black holes. This is a common misconception. He found a mathematical solution. He considered the behavior at the singular radius to be a mathematical curiosity with no physical significance, and every indication we have suggests he would have agreed with Eddington that nature must have some way of preventing such an absurdity. The physical reality of black holes was not established until decades after Schwarzschild's death, through the work of people who were often reluctant to accept their own results. The term black hole would not be coined for another half-century. What Schwarzschild did was hand physics a loaded gun. It took 50 years for anyone to realize it was loaded, and another 50 for them to pull the trigger. To understand why Schwarzschild's result was so unsettling, you need to understand what Einstein had just built. General relativity, in its final form presented on November 25th, 1915, replaced Newton's invisible force of gravity with geometry. Mass and energy curve space-time. Objects moving through curved space-time follow paths that look, to us, like the effects of a gravitational force. The Sun does not pull the Earth. The Sun warps the geometry of the space around it, and the Earth follows the straightest possible path through that warped geometry, which happens to be an ellipse. The mathematics describing this curvature are the Einstein field equations, 10 coupled nonlinear partial differential equations relating the geometry of spacetime on one side to the distribution of mass and energy on the other. The nonlinearity is the killer. It means gravity is a source of gravity. The field itself curves spacetime, which changes the field, which changes the curvature, in an infinite feedback loop that makes the equations viciously difficult to solve. Einstein spent years developing approximation methods, perturbation techniques, ways of sneaking up on answers without ever writing down an exact one. Schwarzschild did not sneak up on anything. He assumed spherical symmetry, no rotation, no electric charge, an empty space around a central mass. Under those assumptions, the 10 equations collapse into something tractable. His solution, written in modern coordinates, describes the geometry of spacetime around any spherically symmetric, non-rotating mass. And the mathematics contain a special radius that depends only on the mass of the central object. This radius, now called the Schwarzschild radius, equals 2 times the gravitational constant times the mass divided by the speed of light squared. For the Sun, that works out to about 3 kilometers. For the Earth, about 9 millimeters, the size of a marble. Think about what that means for the Sun. Every mountain, every ocean, every continent on Earth has a combined mass that is only 1/3 of a millionth of the Sun's mass. The Sun is 333,000 times heavier than Earth, and it is 1.4 million kilometers across. If you could somehow compress all of that, every gram of hydrogen and helium and iron, all 2 non-illion kilograms of it, into a sphere about 3 kilometers across, roughly the distance from one end of a large college campus to the other, or about twice the length of the Golden Gate Bridge's main span, the geometry of space-time around it would become so warped that the Schwarzschild radius would sit at the surface. And at that surface, the mathematics produce a term that goes to infinity. For the Earth, the numbers are even more disorienting. All 6 trillion kilograms, every mountain, every ocean, every continent, every iron molecule in the core, compressed to the size of a marble you could hold between thumb and forefinger, 9 millimeters across. And the space-time around that marble would be permanently, catastrophically warped. Now, Schwarzschild himself did not lose sleep over this. The Sun is not 3 kilometers across. It is 1.4 million kilometers across. The idea of compressing a star below its Schwarzschild radius seemed physically absurd in 1916, and most physicists treated the singular behavior at that radius as a mathematical curiosity, an artifact of the coordinate system, rather than a prediction about nature. This was not an unreasonable position. Coordinate singularities show up everywhere in physics. The North Pole is not a physical singularity just because longitude becomes undefined there. The assumption was that the same kind of thing was happening in Schwarzschild's solution. But there was a second singularity in the mathematics at the dead center, at radius 0, and this one could not be explained away by changing coordinates. If you calculate the Kretschner scalar, a measure of space-time curvature that does not depend on your choice of coordinates, it is perfectly well behaved at the Schwarzschild radius, finite, calm, nothing special. But at radius 0, it diverges to infinity. The curvature of space-time itself becomes infinite. This is not a coordinate artifact. This is the mathematics screaming that something has gone fundamentally wrong with the structure of reality. The physics community spent nearly half a century confused about which of these two singularities was real and which was not. In 1924, Eddington found a coordinate transformation that removed the singularity at the Schwarzschild radius, but he did not fully grasp what he had done. In 1933, Georges Lemaire, the Belgian priest who had already proposed the expanding universe, was the first to explicitly state that the Schwarzschild radius singularity is not physical. But he published in an obscure Belgian journal, and almost nobody noticed. It was not until 1958 that David Finkelstein provided the definitive interpretation. The Schwarzschild surface, he wrote, acts as a perfect unidirectional membrane. Causal influences can cross it, but only in one direction. Things can fall in. Nothing can come out. Einstein himself never accepted this. He believed the Schwarzschild radius was a genuine physical barrier until the day he died in 1955, partly because Lemaitre's paper had been overlooked, partly because the implications were too radical, and partly because Einstein in 1939 published a paper that he believed proved the whole thing was impossible. But before Einstein weighed in, the question of whether gravity could actually win was already destroying a career. In 1930, a 19-year-old Indian physics student named Subramanian Chandrasekhar boarded the SS Pilsner in Madras, bound for Cambridge. He was the nephew of C.V. Raman, who would win the Nobel Prize that very year. Chandrasekhar had entered Presidency College at 15, published his first paper at 18, and was now headed to England with Eddington's book on stellar structure and a paper by Ralph Fowler on the quantum mechanical properties of degenerate matter. The voyage took 18 days. He later described his time at Cambridge as suffocatingly lonely, comparing himself to a single electron in deadly free space, partly due to the isolation of working on ideas nobody else was pursuing, and partly due to the racial prejudice of 1930s England. But by the time the ship docked, he had made one of the most important discoveries in the history of astrophysics. The discovery was this: white dwarf stars, the dense remnants of stars like our Sun, are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that arises because no two electrons can occupy the same quantum state. This pressure has nothing to do with temperature. It is a fundamental consequence of quantum mechanics. Even a completely cold white dwarf is held up by this pressure. But Chandrasekhar applied special relativity to the calculation and found something that Fowler had missed. As a white dwarf gets more massive, the electrons supporting it are forced into higher and higher energy states, approaching the speed of light. And as they approach light speed, the pressure they can exert reaches a maximum. Above a critical mass, roughly 1.44 times the mass of the Sun, electron degeneracy pressure simply cannot hold the star up. Gravity wins. This is the Chandrasekhar limit, and its implications are staggering. Below the limit, a dying star can settle into a stable white dwarf. Above the limit, there is no stable endpoint. The star must continue collapsing. Into what? In 1930, nobody knew. Neutron stars had not yet been proposed. The idea that collapse could continue all the way to the Schwarzschild radius was considered absurd. Chandrasekhar's calculation left a hole in the theory of stellar evolution that nobody wanted to fill. He spent 5 years developing the work with mathematical rigor, and in January of 1935, he was invited to present it at a meeting of the Royal Astronomical Society in London. The night before the meeting, on January 10th, Chandrasekhar dined with Arthur Eddington at the high table of Trinity College. Eddington told him that the secretary of the society had been asked to give Chandrasekhar extra time to speak. What Eddington did not mention was that he had scheduled his own talk immediately afterward, specifically to demolish Chandrasekhar's work. The next day, January 11th, Chandrasekhar presented his rigorous mathematical proof that there was a maximum mass for white dwarf stars. Then Eddington took the podium. He was the most famous astronomer in England, the man who had confirmed Einstein's general relativity with the 1919 solar eclipse expedition. He was charming, eloquent, and absolutely ruthless. He declared Chandrasekhar's relativistic degeneracy formula almost a reductio ad absurdum, compared the result to a child born out of wedlock, and delivered the line that would echo through the history of physics. I think there should be a law of nature to prevent a star from behaving in this absurd way. The audience laughed. Chandrasekhar was not given the opportunity to reply. This was not a scientific disagreement. It was a philosophical one, wearing the costume of science. Eddington had no mathematical error to point to. His objection was that the implication, stars collapsing without limit, was aesthetically unacceptable. Nature should not allow it. Therefore, he believed there must be some undiscovered physical process that prevents it. The pattern continued. At the International Astronomical Union meeting in Paris in July of 1935, before 300 astronomers from 33 countries, Eddington attacked again. Chandrasekhar tried to respond. He sent a note to Henry Norris Russell, the most influential American astronomer, asking for the chance to reply. Russell sent back a note saying he preferred that Chandrasekhar did not, so Chandrasekhar sat in silence, absorbing what he later described as the pitiful glances of the audience. After the session, Eddington approached him and said he was sorry if he had caused hurt. Chandrasekhar asked if Eddington had changed his mind. "No," said Eddington. "Then what are you apologizing for?" Chandrasekhar replied and walked away. Here is the thing that makes this story more than academic politics. Privately, the leading physicists of the era knew Chandrasekhar was right. Niels Bohr and Leon Rosenfeld were, in their words, absolutely unable to see any meaning in Eddington's statements. Pauli agreed with Chandrasekhar. Dirac agreed with Chandrasekhar. But nobody made an authoritative public statement. Nobody stood up at the Royal Astronomical Society and said Eddington was wrong. Eddington's reputation was too large, and the implication of Chandrasekhar's work that gravity has no failsafe, that collapse can proceed without limit, was too disturbing to champion openly. Chandrasekhar left England in late 1936 for the University of Chicago, where he spent the rest of his career. He adopted a remarkable working pattern. Each decade, he would enter a new field of physics, work in it for several years with absolute focus, publish a definitive monograph that became the standard reference, and then move on to something entirely different, 7 complete cycles over a career spanning more than 60 years, covering stellar structure, stellar dynamics, radiative transfer, hydrodynamic stability, ellipsoidal figures of equilibrium, general relativity, and the mathematical theory of black holes. Carl Sagan, who studied at Chicago, recalled, "I learned what true mathematical elegance is from Subrahmanyan Chandrasekhar." In the 1940s, Chandrasekhar drove 100 miles each way through Illinois winter snow to teach a class at Yerkes Observatory that had only 2 students. Those 2 students were Tsung Dao Li and Chen Ning Yang, both of whom would win the Nobel Prize in Physics. Chandrasekhar won the Nobel Prize in Physics in 1983, 48 years after the humiliation, for his theoretical studies of the physical processes of importance to the structure and evolution of the stars. He died on August 21st, 1995, in Chicago. NASA's Chandra X-ray Observatory, launched in 1999, bears his name. Despite everything Eddington did, he maintained a correspondence with the man until Eddington's death in 1944. He even attended cricket and Wimbledon matches with him. And years after Eddington died, Chandrasekhar ranked him alongside Karl Schwarzschild as the greatest astronomers of their time. But what matters for our story is this. Eddington wanted a law of nature to prevent the absurdity. He never found one. Nobody did, because the law does not exist. Einstein tried, though. In October of 1939, he published a paper in the Annals of Mathematics, arguing that objects could not be compressed below their Schwarzschild radius. His model was a cluster of particles orbiting a central point. As the orbits shrink toward the critical radius, the orbital velocities approach the speed of light. Since nothing with mass can reach light speed, Einstein concluded that matter cannot be concentrated arbitrarily. The Schwarzschild singularity, he wrote, does not appear for the reason that matter cannot be concentrated arbitrarily, and this is due to the fact that otherwise the constituting particles would reach the velocity of light. Einstein was wrong. He was wrong on 2 counts. First, he was still confusing the coordinate singularity at the Schwarzschild radius with a physical barrier. Second, and more fundamentally, his model assumed circular orbits. It assumed equilibrium. It assumed that matter would try to form stable configurations as it collapsed. But gravitational collapse is not an equilibrium process. It is dynamic, catastrophic, and unstoppable once it begins. The same month Einstein published his rejection, someone else published the proof. On September 1st, 1939, the day Nazi Germany invaded Poland, Robert Oppenheimer and his student Hartland Snyder published a paper in Physical Review titled On Continued Gravitational Contraction. They showed, using general relativity without approximation, that a sufficiently massive star with no internal pressure will collapse indefinitely. The star thus tends to close itself off from any communication with a distant observer. They wrote, only its gravitational field persists. Kip Thorne later assessed the paper with a clarity that underscores its importance. It stands up completely. There are no flaws. It went so far beyond anything that anybody else had ever done. Oppenheimer and Snyder had not just shown that collapse was possible. They had shown what it looks like from both sides. From the perspective of a distant observer, the surface of the collapsing star slows as it approaches the Schwarzschild radius, redshifts, and fades to invisibility, taking an infinite amount of external time to reach the horizon. But from the perspective of someone riding the surface, the collapse passes through the Schwarzschild radius in finite time and continues to the singularity. Both descriptions are correct. They are the same physical event seen from different frames of reference, and the implication was unavoidable. A star that collapses crosses its own Schwarzschild radius and disappears from the observable universe, leaving behind only gravity. The exterior geometry is exactly Schwarzschild's solution, but nobody noticed. On the same day, literally the same day, Niels Bohr and John Wheeler published their landmark paper on nuclear fission in the same journal. Fission had obvious, immediate, terrifying practical implications. Gravitational collapse was speculative and abstract. The Oppenheimer-Snyder paper vanished. The Second World War consumed the physics community. Oppenheimer became director of the Manhattan Project. He never returned to black hole research. Years later, in 1963, at the first Texas Symposium on relativistic astrophysics in Dallas, John Wheeler gave an enthusiastic lecture championing Oppenheimer's early work on gravitational collapse. Oppenheimer was at the conference. He did not attend Wheeler's lecture. He sat on a bench outside the lecture hall, chatting with friends about other things. He died on February 18th, 1967, months before Wheeler coined the term that would define the legacy of his own greatest paper. Freeman Dyson considered the Oppenheimer-Snyder paper Oppenheimer's greatest contribution to science, greater than anything he did during the Manhattan Project. So by 1939, the mathematics was settled. Schwarzschild had provided the exact exterior solution. Chandrasekhar had shown that above a critical mass, quantum degeneracy pressure fails. Oppenheimer and Snyder had shown that collapse proceeds to the Schwarzschild radius and beyond. And the question, is there anything that can prevent gravity from winning, had been answered? No, there is not. But the physics community did not accept this. The war scattered everyone. The Cold War redirected their energies. General relativity was considered a mathematical backwater, elegant but impractical, a theory with no experimental consequences that could be measured with existing technology. Einstein himself, the theory's creator, spent his last decades at Princeton pursuing a unified field theory that went nowhere. The few people who worked on general relativity were considered, as Thomas Gold would later put it, magnificent cultural ornaments who might never be useful to science. The number of active researchers in the field worldwide could fit comfortably in a single lecture hall. The idea that Schwarzschild's solution described real objects in the real universe was not taken seriously by the mainstream physics community. There is an irony here that is worth pausing on. During the same decades that general relativity was being ignored, nuclear physics and quantum mechanics were producing transistors, computers, nuclear reactors, and hydrogen bombs. Physics was transforming civilization, and the one branch of physics that dealt with the most extreme environments in the universe, the places where space-time itself breaks, was considered an intellectual curiosity with no practical relevance. It took the universe itself to force a correction. That correction came in the 1960s, and it came fast. In 1963, astronomers discovered quasars, quasi-stellar radio sources, at cosmological distances billions of light years away, radiating more energy than entire galaxies from a volume no larger than the solar system. The energy output was staggering. Some quasars were producing the luminosity of 100 trillion suns from a region you could fit inside our solar system. No known physical process could explain this except one: gravitational collapse. Matter falling into something so compact, so deep in a gravitational well, that the conversion of gravitational potential energy to radiation dwarfed nuclear fusion by orders of magnitude. Nuclear fusion converts less than 1% of rest mass energy. Gravitational accretion onto a black hole can convert 5 to 40% depending on the spin. Suddenly, gravitationally collapsed objects were not abstract mathematical curiosities. They were the only viable explanation for the brightest objects in the universe. That same year, at the first Texas Symposium on Relativistic Astrophysics in Dallas, with about 300 attendees, a young New Zealand mathematician named Roy Kerr presented an exact solution to Einstein's equations for a rotating mass. This was the realistic generalization of Schwarzschild's solution, because real objects rotate. A collapsing star carries angular momentum, and that angular momentum does not disappear at the horizon. Kerr's solution described a rotating black hole with two horizons and an ergosphere, a region outside the outer horizon where spacetime itself is dragged along by the rotation so violently that nothing can remain stationary, not even light orbiting in the direction opposite the spin. The significance of Kerr's solution was not immediately grasped at the conference, but it would become one of the most important exact solutions in all of general relativity, because every black hole that forms from a collapsing star almost certainly rotates. Then came the result that destroyed the last escape route. In 1965, Roger Penrose proved a theorem. It said, in essence, that if a trapped surface forms, if you get a closed two-dimensional surface where all light rays, even those pointing outward, are converging toward the center, then a singularity is inevitable. Not because of symmetry assumptions, not because of idealized models, not because of any special choice of matter distribution. Inevitable, under the most general conditions physically possible. This was the result Eddington had dreaded. Every previous demonstration of gravitational collapse relied on perfect spherical symmetry. You could always argue, and people did argue, that the slightest asymmetry in a real collapsing star would cause matter to miss the center, bounce off itself, and avoid the singularity. Penrose killed that argument. His theorem uses topology, not symmetry. Once a trapped surface forms, the global structure of spacetime guarantees a singularity regardless of how lumpy, asymmetric, or chaotic the collapse is. Penrose recalled that the insight came while crossing a road with a colleague named Ivor Robinson. He stopped talking as we were watching out for traffic. And then, when he left, I had this strange feeling of elation. This idea was the crucial characterization of when a collapse had reached a point of no return. The idea cost him a momentary lapse in road safety and won him the 2020 Nobel Prize in Physics 55 years later for the discovery that black hole formation is a robust prediction of the general theory of relativity. With Penrose's theorem, the mathematical case was closed. No special symmetry needed. No idealized matter distributions. If enough mass accumulates in a small enough region, a trapped surface forms. And from that moment, the singularity is mathematically guaranteed. There is no escape route. Eddington's hoped-for law of nature does not exist. Stephen Hawking extended Penrose's techniques in a different direction, proving singularity theorems for cosmology and collaborating with Penrose on the Penrose-Hawking theorems that established singularities as generic features of general relativity. But Hawking's most extraordinary contribution to black hole physics came in 1971, when he proved the area theorem, which states that the total surface area of a black hole's event horizon can never decrease. This looked suspiciously like the second law of thermodynamics, where entropy never decreases. Jacob Bekenstein took the analogy seriously and proposed that black holes actually possess entropy proportional to their horizon area. Hawking initially resisted this idea. If black holes have entropy, they must have temperature. And if they have temperature, they must radiate. But nothing escapes a black hole. So how could they radiate? Hawking sat down to disprove Bekenstein and ended up proving him right. But what do you call the thing that forms? For years, Soviet physicists used the term frozen star, because from a distant observer's perspective, the collapsing matter appears to freeze at the Schwarzschild radius, redshifting into invisibility. Yakov Zeldovich and Igor Novikov were leading this work in Russia, and Zeldovich and a colleague named O.H. Gusainov became the first to systematically search for black hole candidates in binary star systems. Western physicists talked about gravitationally completely collapsed objects, which is accurate but impossible to say at a conference without losing your audience. John Wheeler changed that. In his autobiography, Wheeler recalled that at a conference, he kept using the phrase gravitationally completely collapsed object until someone in the audience called out, "How about black hole?" Wheeler wrote, "I had been searching for just the right term for months, mulling it over in bed, in the bathtub, in my car, wherever I had quiet moments. Suddenly, this name seemed exactly right." His first formal published use came in a lecture on December 29th, 1967. The term stuck. Wheeler also offered the poetry. The star, like the Cheshire Cat, fades from view. One leaves behind only its grin, the other only its gravitational attraction. He noted with amusement that the French translation is so obscene that French publishers resisted it vigorously, to no avail. Beyond black hole, Wheeler coined wormhole, quantum foam, it from bit, and the phrase "a black hole has no hair," referring to the no-hair theorem, which states that a settled black hole is completely described by just three numbers: mass, charge, and angular momentum. Wheeler's journey with this idea is worth pausing on, because he was not always a believer. At the 1958 Solvay conference, he had argued that the Oppenheimer-Snyder model was too idealized, that realistic collapse with nuclear physics, with pressure, with radiation, would behave differently. What changed his mind was brutally practical. Edward Teller told him about computer simulations by Sterling Colgate at Lawrence Livermore National Laboratory. Colgate had adapted thermonuclear bomb codes to simulate stellar implosion. The simulations confirmed that even with realistic physics, collapse proceeds exactly as Oppenheimer and Snyder had predicted. The bomb codes, designed to model the most violent explosions humans had ever created, showed that gravity is more violent still. Wheeler spent the rest of his career as the most passionate champion of black hole physics. training an entire generation of physicists, including Kip Thorne, who would later co-found LIGO. Thorne recalled their first meeting. He greeted me with a warm smile and began immediately, as though I were an esteemed colleague, not a total novice, to discuss the mysteries of gravitational collapse. I emerged an hour later, a convert and disciple. Then came Hawking. His 1974 paper, Black Hole Explosions. In the journal, Nature may be the most important paper on black holes since Schwarzschild's. The question mark in the title was almost playful given what the paper contained. Hawking showed that quantum effects near the event horizon cause black holes to emit thermal radiation. The mechanism involves the uncertainty principle and the seething quantum vacuum near the horizon. But the result is clean and devastating. Black holes are not perfectly black. They glow faintly with a temperature inversely proportional to their mass. For a black hole with the mass of the Sun, that temperature is about 100 millionth of a Kelvin. To put that in perspective, the cosmic microwave background, the afterglow of the Big Bang that fills the entire universe, has a temperature of 2.7 Kelvin. That is roughly 200 million times hotter than a solar mass black hole. So, a solar mass black hole is currently absorbing vastly more energy from its environment than it is radiating. It is getting bigger, not smaller. But in principle, given a universe that keeps expanding and cooling, there will come a time when the cosmic background temperature drops below the black hole's temperature, and at that point, the black hole will begin to shrink. It will evaporate. A solar mass black hole would take roughly 10 to the power of 67 years to evaporate completely. For scale, the current age of the universe is about 1.4 times 10 to the 10th years. So, a solar mass black hole's evaporation time is 10 to the 57th times the current age of the universe. That number is so large, it does not translate to any human intuition. But it is finite. Given enough time, even black holes die. This raised a new problem so profound that it consumed theoretical physics for decades and arguably still does. If a black hole evaporates, what happens to the information that fell in? Quantum mechanics demands that information is conserved. The evolution of any quantum system must be reversible in principle. You might scramble information beyond any hope of practical recovery, but the laws of physics say it must still exist in some form. But Hawking radiation appears to be perfectly thermal, perfectly random, containing no information about what the black hole swallowed. If this is correct, quantum mechanics is broken at the most fundamental level. If it is wrong, our understanding of black holes is broken. Either way, Schwarzschild's century-old solution was still generating crises. Hawking put it memorably. Not only does God play dice, but he sometimes confuses us by throwing them where they can't be seen. He also offered the observation that one could well say of the event horizon what the poet Dante said of the entrance to hell: all hope abandon, ye who enter here. Hawking himself bet on information being lost. In February of 1997, he and Kip Thorne wagered against John Preskill of Caltech that information falling into a black hole is permanently destroyed. Hawking conceded in July of 2004 at a conference in Dublin, presenting Preskill with a baseball encyclopedia from which information can be retrieved at will. But Thorne did not concede, and the information paradox, as of today, is still not resolved to everyone's satisfaction. it remains one of the deepest open problems in theoretical physics, sitting precisely at the intersection of quantum mechanics and general relativity, exactly where most physicists expect the next fundamental revolution to occur. So by the mid-1970s, the theoretical picture was extraordinary. Schwarzschild's solution described the geometry outside any non-rotating, collapsed object. Kerr's described rotating ones. Penrose had proven that singularities are inevitable. Hawking had shown that black holes radiate and evaporate. The no-hair theorem established that a settled black hole is completely described by just three numbers: mass, charge, and angular momentum, meaning that all the complexity of whatever fell in is erased. Every theoretical attack on the question, every attempt to find a law of nature that prevents gravity from winning, had failed. But nobody had ever seen one. Every conclusion, every prediction, every theorem rested on mathematics and logic. The universe had not yet been asked directly whether these objects exist. That was about to change, and the answer would come from multiple directions at once. The first strong candidate was Cygnus X-1, detected in 1964 during a sounding rocket flight from White Sands, New Mexico. The Uhuru satellite measured rapid X-ray fluctuations in 1970, indicating a compact source. By 1971, radio observations had pinpointed the source to a blue supergiant star called HDE 2-26868. In 1972, two independent teams, Louise Webster and Paul Murden at Greenwich and Charles Thomas Bolton in Toronto, announced that the supergiant had an invisible companion too massive to be a neutron star. Hawking and Thorne made a bet, written on December 10, 1974, and framed on Thorne's office wall. It reads, "Whereas Stephen Hawking has a large investment in general relativity and black holes and desires an insurance policy, and whereas Kip Thorne likes to live dangerously without an insurance policy, therefore, be it resolved that Stephen Hawking bets 1 year's subscription to Penthouse against Kip Thorne's wager of a 4-year subscription to Private Eye, that Cygnus X-1 does not contain a black hole of mass above the Chandrasekhar limit." Hawking explained the logic in a brief history of time. "This was a form of insurance policy for me. I have done a lot of work on black holes, and it would all be wasted if it turned out that black holes do not exist. But in that case, I would have the consolation of winning my bet." He conceded in June of 1990. Thorne recalled, "Stephen and an entourage of family, nurses, and friends broke into my office at Caltech, found the framed bet, and wrote a concessionary note on it, with validation by Stephen's thumbprint. Hawking later noted that he paid the specified penalty, which was a 1-year subscription to Penthouse, to the outrage of Kip's liberated wife. A 2021 study revised the mass of Cygnus X-1's black hole to 21.2 solar masses, making it the heaviest stellar mass black hole ever measured by electromagnetic radiation. It spins at roughly 800 rotations per second. But individual candidates were not enough. What physicists really wanted was a way to study the extreme gravitational environment near a black hole. That required something much closer to home. In February of 1974, Bruce Ballack and Robert Brown detected a compact radio source at the exact center of the Milky Way, using the National Radio Astronomy Observatory's interferometer at Green Bank, West Virginia. In 1982, Brown gave it a name, Sagittarius A star. He borrowed the asterisk from atomic physics, where it denotes an excited state, because he found the source exciting. Starting in the early 1990s, two independent groups set out to prove that Sagittarius A star was a supermassive black hole by tracking the orbits of stars around it. Andrea Ghez at UCLA used the Keck Observatory in Hawaii with adaptive optics, technology that deforms a telescope's mirror hundreds of times per second to correct for atmospheric turbulence, turning a blurred mess into a sharp point of light. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics pursued parallel work using the European Southern Observatory's telescopes in Chile with similar technology. Both groups were doing something that seemed impossible. They were watching individual stars orbit an invisible object 26,000 light-years away, tracking their positions year after year with exquisite precision and computing the mass of the thing they were circling. Their key target was a star called S2, which orbits Sagittarius A star with a period of roughly 16 years, swooping within about 17 light hours of the center at closest approach, roughly 120 times the Earth-Sun distance. That sounds like a lot until you remember what it is orbiting. At closest approach, S2 moves at roughly 2.5% the speed of light, about 7,500 kilometers per second, and its orbit matches perfectly with what general relativity predicts for a star orbiting a mass of 4 million suns. In 2000, Gez's team reported the first detection of stars accelerating around the invisible mass, proving it was not a distributed cloud of dark matter, but a single, compact object. In October of 2002, Genzel's team published orbital dynamics requiring a central mass of 4.1 million solar masses confined within 17 light hours, 4 million times the mass of our Sun, compressed into a region smaller than our solar system. The Schwarzschild radius for that mass works out to about 12.7 million kilometers, roughly 31 times the diameter of the Sun. Everything that holds 4 million stars worth of mass crammed inside Mercury's orbit. In 2019, Ghez published the most comprehensive test of general relativity near a supermassive black hole, measuring the gravitational redshift of light from S2 as it whipped past Sagittarius A star. Her conclusion: Einstein's right, at least for now. The for now is the mark of a real scientist. Every measurement is a chance for general relativity to break. It has not broken yet. She and Genzel shared the 2020 Nobel Prize in Physics with Roger Penrose, Ghez, and Genzel for the discovery of a supermassive compact object at the center of our galaxy. Penrose for proving that black holes are an inevitable prediction of general relativity. But even orbital tracking is indirect. You are watching stars react to something you cannot see. What the world wanted was a picture. On April 10th, 2019, the Event Horizon Telescope collaboration announced the first image of a black hole. Not the black hole itself, of course. You cannot photograph darkness. What they imaged was the bright ring of superheated material orbiting just outside the event horizon of M87 star, a supermassive black hole at the center of the galaxy, Messier 87, roughly 53 million light-years away. The image showed an asymmetric bright emission ring surrounding a dark central shadow, exactly as general relativity predicted. Shepard Doeleman, the founding director of the EHT, said it plainly: "We have achieved something presumed to be impossible just a generation ago." The technical achievement is almost as staggering as the scientific one. The EHT linked 8 radio telescopes at 6 locations across the globe, from the ALMA array in the Chilean Atacama Desert to the South Pole Telescope in Antarctica, from observatories atop Mauna Kea in Hawaii to a dish in the mountains of Spain. They observed at a wavelength of 1.3 millimeters to create a virtual telescope the size of Earth. The observations were taken on 4 nights in April of 2017. The data was so voluminous, petabytes of raw measurement, that it could not be transmitted over the internet. It was physically shipped on crates of hard drives via commercial air freight to processing centers at MIT and the Max Planck Institute. Katie Booman, then a postdoctoral researcher and now on faculty at Caltech, led the development of one of 4 independent imaging pipelines. Her photograph, reacting to the first image on her laptop screen, became one of the iconic images of 21st century science. The angular resolution required was equivalent to reading a newspaper in New York from a cafe in Paris, or, as the European Southern Observatory put it, resolving a donut sitting on the surface of the moon. Now think about the object they photographed. M87 star has a mass of roughly 6.5 billion solar masses, 6.5 billion times the mass of our Sun. Its event horizon spans about 120 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. That means the event horizon of M87 star is roughly 3 times the size of Pluto's entire orbit around the Sun. Voyager 1, the most distant human-made object at about 160 astronomical units from Earth, would be inside its event horizon. A beam of light takes about 2.5 days just to cross its shadow. And to make this even more disorienting, its average density, if you calculate mass divided by the volume inside the Schwarzschild radius, is about 0.44 kilograms per cubic meter. That is less dense than air at sea level. You could in theory be floating in air thinner than a mountaintop and already be inside a black hole, past the point of no return, heading inevitably toward a singularity. The event horizon is not a surface. It is not a wall. It is a boundary in the causal structure of spacetime. And for supermassive black holes, there is nothing locally remarkable about crossing it. The horror is purely geometric. Compare this to the black hole at the center of our own galaxy, Sagittarius A star, at roughly 4 million solar masses, is more than 1,000 times less massive than M87 star. Its event horizon is about 12.7 million kilometers across, roughly 31 times wider than the Sun. If Sagittarius A star were the size of a donut, M87 star would be the size of a football stadium. 3 years later, on May 12, 2022, the EHT released an image of Sagittarius A star, the black hole at the center of our own galaxy. The challenge was far greater. Sagittarius A star is roughly 1,500 times smaller than M87 star, which means the gas orbiting it changes configuration in minutes rather than weeks. EHT member Vincent Fish described the difficulty. Sagittarius, a star is changing over minutes, so the data is jumping all over the place. It took 5 years from observation to publication, but the image confirmed the same ring structure, the same shadow, the same geometry predicted by Schwarzschild's solution more than a century earlier. Sarah Markov, co-chair of the EHT Science Council, captured the significance. We have two completely different types of galaxies and two very different black hole masses, but close to the edge of these black holes, they look amazingly similar. This tells us that general relativity governs these objects up close. Then LIGO heard them. On September 14th, 2015, at 9:50 a.m. Universal Time, the Laser Interferometer Gravitational Wave Observatory detected a signal that had traveled 1.3 billion light-years. Two black holes, one of roughly 36 solar masses and one of roughly 29, had spiraled toward each other for millions of years, their orbits decaying as they radiated gravitational energy until in the final fraction of a second, they plunged together and merged into a single black hole of about 62 solar masses. The missing 3 solar masses, 3 times the mass of our Sun, had been converted entirely into gravitational wave energy and radiated outward at the speed of light in every direction. 3 solar masses, gone, not converted into heat or light or particles, converted into ripples in the fabric of spacetime itself. The peak power output during that final fraction of a second exceeded 3.6 times 10 to the 49th watts. That is greater than the combined luminosity of every star in the observable universe at that instant. For a brief moment, the collision of 2 black holes outshone everything else in creation, but it outshone them in a form of energy that no eye can see and no telescope before LIGO could detect. The signal was a chirp, a rising tone sweeping from 35 Hz to 250 Hz in about 1/5 of a second. If you played it through a speaker, you could hear it, a rising whoop that compresses 1 million years of orbital decay into a sound shorter than a heartbeat. The detector arms, each 4 kilometers long, changed length by 1,000th of the width of a proton. Think about that measurement for a second. A proton is roughly 10 to the minus 15 meters across. LIGO measured a change of 10 to the minus 18 meters. That is like measuring the distance from Earth to the nearest star and detecting a change the width of a human hair. Signal-to-noise ratio was 24. The false alarm rate was less than 1 event per 203,000 years. This was not noise. This was the sound of space-time ringing like a bell as 2 regions of infinite curvature became one. The 2017 Nobel Prize in Physics went to Rainer Weiss, Barry Barish, and Kip Thorne for their contributions to LIGO. Wheeler had died in 2008, 9 years too soon to see the machine his student helped build detect the objects he named. As of 2025, approximately 300 black hole mergers have been observed by LIGO and its partner observatories. 300, each one a pair of objects that Einstein said could not exist, spiraling together and combining in events that outshine the entire visible universe for a fraction of a second. On August 17th, 2017, LIGO and the Virgo detector in Italy observed something different. The merger of 2 neutron stars, the first ever detected via gravitational waves. A gamma-ray burst arrived 1.7 seconds later. Optical telescopes found the source in a galaxy called NGC 4993, about 130 million light-years away. The merger produced roughly 16,000 Earth masses of heavy elements, including roughly 10 Earth masses worth of gold and platinum. Much of the gold on Earth was forged in collisions like this one, billions of years ago. That observation was named Science magazine's Breakthrough of the Year for 2017. The most massive merger yet observed, detected in November 2023, produced a black hole of roughly 225 solar masses, and the clearest signal ever, detected in January 2025 with a signal-to-noise ratio of about 80, provided the first confirmed detection of a Kerr overtone, essentially hearing the newly formed black hole ring like a struck bell in the specific frequencies that Kerr's 1963 solution predicted, and delivered empirical confirmation of Hawking's area theorem. A theoretical result from 1971, derived by a 29-year-old in a wheelchair using pure mathematics, confirmed by a laser interferometer measuring disturbances smaller than a proton, 60 years after the theorem was proven, and a century after the solution that started it all. There is a misconception that needs correcting here, because it shapes how people think about all of this. Black holes do not suck. This is probably the single most persistent misunderstanding in all of popular science. They are not cosmic vacuum cleaners pulling everything toward them with some exotic force. If you replace the sun with a black hole of identical mass right now, this instant, the Earth's orbit would not change at all. Not 1 millimeter. The gravitational field at our distance would be exactly the same. The planets would continue their orbits as if nothing happened. It would get very dark and very cold, obviously, because the sun would no longer be emitting light, but the gravitational situation would be unchanged. Black holes exert the same gravitational force as any object of equal mass at the same distance. There is nothing special about their gravity at large distances. NASA astrophysicist Ryan Chornock compared them to Venus flytraps. They wait for objects to come to them. The danger is only at close range, specifically within or near the event horizon, and the experience of falling in depends entirely on the mass, which leads to the second misconception worth clearing up. People imagine that approaching a black hole means being crushed. For a stellar mass black hole, with a Schwarzschild radius of perhaps 30 kilometers, this is roughly correct, though the process is more dramatic than simple crushing. Tidal forces, the difference in gravitational pull between your head and your feet, would stretch you along the radial direction and compress you laterally, pulling you into a thin stream of atoms, a process physicists cheerfully call spaghettification. For a stellar mass black hole, this would happen hundreds of kilometers before you even reach the horizon. But for a supermassive black hole, like Sagittarius A star, with an event horizon 12.7 million kilometers across, the story is completely different. Tidal forces at the horizon are negligible. The event horizon is so large relative to the curvature that locally, spacetime appears flat there, just as the surface of the Earth appears flat at human scales, despite being curved at planetary scales. You could cross the event horizon of a supermassive black hole without any physical sensation at all. No wall, no barrier, no sign. Glenn Starkman of Case Western Reserve University noted that the astronaut crossing the supermassive black hole should enjoy the trip, at least until the tidal forces catch up deeper inside, which for Sagittarius A star gives you approximately 20 seconds between crossing the horizon and reaching the singularity. Now consider the arc of this story, because the arc itself is as remarkable as the physics. In 1916, a dying soldier on a battlefield found an exact solution to the most complicated equations in physics. That solution contained a prediction so extreme that the man who wrote the equations, Einstein himself, refused to believe it. The most famous astronomer in England tried to bully a 19-year-old out of pursuing its implications, and the scientific establishment stood by and watched. A paper proving it was physically real was published on the day the Second World War began and was promptly buried by the apocalypse. The man who wrote that paper became the father of the atomic bomb and never looked at gravitational collapse again, sitting on a bench outside the lecture hall when others championed his greatest work. For decades, the entire subject was considered a backwater, a playground for mathematicians, with no connection to the physical universe, funded poorly, staffed sparsely, and dismissed by the most powerful voices in the field. And then the universe spoke. Quasars screamed with the energy of infalling matter. Pulsars proved that compact objects exist. Stars at the center of our galaxy traced orbits around invisible masses of 4 million suns. Telescopes spanning the entire globe, from Antarctica to the Atacama Desert, produced photographs of the shadows these objects cast on the light behind them. And 2 4-kilometer laser beams, sensitive to disturbances 1,000 times smaller than a proton, recorded the sound of 2 such objects colliding 1 billion years ago, converting 3 solar masses into ripples in the geometry of space and time. Every objection was answered, every escape route closed, every hoped for law of nature that might prevent the absurdity, every argument that the singularity was just a mathematical artifact, every model that tried to find a stable endpoint for massive stellar collapse turned out to be wrong. There is one more thing worth knowing about Karl Schwarzschild. He had 3 children. His daughter Agatha fled Nazi Germany in 1933 and eventually became a professor of classics in New Zealand. Her passage to England was supported by Cecilia Payne-Gaposchkin and financed anonymously by Arthur Eddington, the same Eddington who would later try to suppress the implications of her father's work. His son Alfred stayed in Germany and was murdered in the Holocaust in 1944, and his son Martin became one of the most important astrophysicists of the 20th century. Martin Schwarzschild left Germany in 1936, served in US Army intelligence during the Second World War, earning the Legion of Merit and the Bronze Star, and joined Princeton University in 1947 at the invitation of Lyman Spitzer Jr. With John von Neumann, he was among the first to use digital computers for scientific research, computing models of stellar evolution on machines that filled entire rooms. He led the stratoscope balloon telescope projects that produced the first sharp astronomical photographs from above Earth's atmosphere, proving that telescopes lifted beyond the turbulence of the atmosphere could see the universe with extraordinary clarity, an insight that ultimately led to the Hubble Space Telescope. He published the definitive textbook on stellar structure and evolution. He was elected president of the American Astronomical Society, and in 1959, he became the first recipient of the Karl Schwarzschild Medal, named for his father. He received the National Medal of Science in 1997, the year he died. Martin Schwarzschild spent his career studying the insides of stars. He spent his career studying the process by which stars exhaust their fuel, contract, and, if massive enough, collapse. He spent his career, in other words, working out the physical reality of the mathematics his father had written down in a trench under fire, while his own body was consuming itself. Karl Schwarzschild never knew what his solution meant. He thought the singular point was a mathematical curiosity. He could not have imagined that it described real objects scattered throughout the universe by the billions, that the largest of them contain the mass of tens of billions of suns, that the smallest of them form in the violent deaths of massive stars, that we would one day photograph their shadows from 53 million light-years away and listen to the sound of them colliding from over a billion. He could not have imagined that his exact solution, found in weeks, would be confirmed by every observation anyone has ever made, from stellar orbits at the galactic center to the ringing of merged horizons detected by lasers sensitive to 1,000th of a proton's width. He wrote to Einstein that the war had treated him kindly enough to allow a walk in the land of ideas. The walk lasted a century. The ideas turned out to be real, and the land turned out to be stranger, more beautiful, and more terrifying than anyone who set foot in it could have possibly imagined.